Hey everyone. I'm just going to talk a little bit about some of the kind of challenges and details that we're working through here. So I think the first main challenge right now in the availability of this material is it does come in smaller cables, so not the same scale of rods that we would typically be used to. So what we're working on now is how to transition from a larger steel rod into a device of multiple smaller cables where we can use this material and get really good performance from that material. So here's what we would look at maybe on a larger scale device, like similar to what we would put into the Bechtel project. And a little more detail here. And working with Tri-Pyramid, who does a lot of the kind of architecturally exposed bracing to bring in a level of refinement to it. And as you can kind of see here on the right end, an embedded turnbuckle so that the system can be pre-tensioned without a kind of big obtrusive turnbuckle on the end. And then the other main challenge we're working on is how to take all these smaller cables and provide a reliable anchor at the end that's also very minimal and small in profile. So we're working again with Tri-Pyramid on the swaging of these cables that transitions it to just a threaded end with just a nut at the end. And here's just a prototype in their lab right now, what that looks like with the silver swage, and then you can see the nuts at the end. On the analysis side, we're also learning a lot. One of the challenges, modeling in SAP or ETABS is there's not a way to model this kind of flag-shaped hysteretic behavior. Luckily, there was a paper in the AC Journal of Structural Engineering from a couple years ago that we were able to build off of, and a lot of our engineers who are here have been working on this, but essentially it's made up of each SMA device in our nonlinear model is made up of 5 link elements, multiple multilinear elastic elements, hooks and springs, and then a plastic element. And then when putting those all together in some in series, some in parallel, you can actually recreate the behavior that we're looking for very well. So here's our earlier test based on some early physical test results. We were able to match very closely by tuning these 5 links. And then here's where we are now. The gray in the back is our most recent cyclic test of these cables. And you can see a kind of slope that's formed by the kind of angle of the assembly of this cable. And then the black or the dark is our current analysis matching that. So a couple more things just to note, and they'll come important to the goals of this test. Rupa's mentioning the point of hardening, which for this sample is around 5.5% strain. So our current design is to stay below that. And so that's that red line there. And so our tests that we're doing here are all kind of targeting right around there, maybe a little below or a little over. And then in terms of an overstrength design, by staying below the hardening, and then with the appropriate overstrength, all attachments and components would be designed for that blue line there. So Rupa's now going to talk a little bit more about the specifics of the tests.
So we know all about this repeat frame, and that is something that was offered by Khaled when we started talking about the shaking table test. For us, it was only bringing in the rods and the SMA devices that, along with the gusset plates, which could be attached to this frame and be tested on. And this frame is basically a 3-story frame that we have in here at the lab, which you'll be seeing in a few minutes. It's 8-foot bay. It's a north frame and the south frame. On the other direction, we are not applying the ground motion, so that is a regular concentric braced frame system with angles. And because we are going to be doing this scale test, each device has only 3 cables, and we put in there 3 cables because that was the only that amount of material was the only material that we had readily available, which we could have bought, and we could have put this into 12 devices. And Tri-Pyramid engineered this elegant solution where the anchor, the nut ends, are completely concealed in the end devices. And yesterday when we were doing our sine wave test, white noise test, and we also ran one ground motion, we actually completely dismantled this particular device and figured out how to do it. So if we can do it, definitely anybody can do it. I mean, I was there, so I could do it. Anybody could do it. So we feel pretty comfortable. Very elegant solution here. And then, what goes? And these was how these devices were shipped into the lab, and they contained these wooden rods. And the mechanism was such that they were these cables were pre-strained and then brought into the lab. We attach the rod to it, put in the clevises, and when we tighten the clevises to a certain point, and the rod is in that bit of a tension, the wooden rods pop off. So it's a nice way of just making that happen. But in the lab, we also had the strain gauges to measure that and make sure that indeed in the cables we have the pre-strain that we were asking them to put on. So here is our shake table test analysis model that Yang has been furiously working on, measuring the period of the structure and trying to again input it and rerunning the analysis with different ground motions. And we looked into 10 different ground motions. We ran one of them yesterday, the Loma Prieta one. These are the 10 ground motion that we are studying at the moment, and either today, tomorrow, or in the next week, we are going to run most of them. Today, we think we are going to run the Kobe as well as the Cocelli. You're very familiar with those ground motions if you are in this engineering field here. We expect that the amount of strain that we see in this devices isn't going to be in the order of 5.5%, because the frame turned out to be a little softer than what we had anticipated it to be. Because, and we can clearly relate to the fact that when we model in the ETABS or any analysis model as a complete fixed connection, nothing is completely fixed. It has some flexibility to it. Nevertheless, we expect the behavior to be such that in each of the devices will follow the hysteresis that we are looking for in here. We would perhaps see a drift in the range of 4.5%. We'll check on that today. And with that, we will have Michael conclude us for.
Thank you. I just want to recognize many of the people who've been involved in this, and actually many are in the room here, so thank you very much for that. And our collaboration partners, but particularly PEER, who's made this possible. One of the really wonderful things about today is it gives me and our team a little perspective on how far we've come in 50 years. And we realize that we are just part of a continuum that's happening, and perhaps we can add our little bit of research to the mountain that Professor Masalam has described, and carry on. So 941 perhaps. So thank you very much.